Welcome back. Hopefully you have watched Chapter 6, Part 1. If you didn't, stop now. Watch that first. These two lectures they could almost be two separate chapters, to be completely honest. Part 1, we introduced the idea of ionic and covalent bonds, ionic and covalent compounds. And then we talked about naming, writing formulas, positive ions, negative ions, things like that. In this part of Chapter 6, we're going to be talking about some of the characteristics of these compounds. We're going to cover electronegativity, we're going to cover Lewis structures for compounds, and some other things that we can get some information from these different chemical formulas. We're going to start with writing Lewis structures for molecules and polyatomic ions. The simplest molecule that you can have is a hydrogen molecule. It's just two hydrogens bonded together. To form this molecule, the atoms have to move closer together. And the positive charge from the nucleus of one hydrogen atom attracts the electron of the other hydrogen atom. They share their electron, they each have one electron, in a covalent bond so that they have a noble gas arrangement that looks like helium. So they're happy to be this way. When they form this molecule, it's more stable than just two individual hydrogen atoms. So that's why you get the formation of molecules, stability. This is just a graphic of how a molecule forms. So you've got two hydrogen atoms that are far apart, they're not attracted to each other. Then, by chance, they both happen to go to the same store at the mall at the same time. And attraction pulls them closer. So you've got the nucleus that's positively charged in one atom attracting the electron in the other atom, and vice versa. So they're being pulled closer and closer together until they're close enough to share electrons. That's when they form a molecule. So the distance between the nuclei of the two hydrogen atoms decreases the closer they get together. And when they form that molecule, they're as close as they're going to be. Likewise, as they get closer together, the energy decreases. So this H2 molecule is lower in energy than these two hydrogen atoms. We can use Lewis structures to represent molecules. So we talked about Lewis structures in the last chapter, but we were drawing them for valence electrons for just individual atoms. Now we're going to take that information and move it forward to draw structures for molecules. The electrons in a molecule are shared. So those shared electrons are called bonding pairs. And you can show them as two dots, like this, or a single line. The non-bonding pairs, so the electrons that are not doing anything, they're not being shared, those are called lone pairs. And they're placed on the outside of the atom. So you can see here, that is a lone pair above the nitrogen. But each of these lines between the nitrogen and the hydrogen, that is a bonding pair. The other way that you could show this would be with dots, but we typically replace these dots. I'll circle them. The ones that are circled in red, those are what we replace with single lines. So that's a Lewis structure. Let's start drawing one. Let's say that we want to draw the formula for a molecule of fluorine, which is F2. You're going to start by just drawing the dot symbol for a fluorine atom. And to refresh your memory, to do that, you have to figure out how many valence electrons there are. And the trend for the representative elements is that you can look at the group number that has the A behind it, and that tells you how many valence electrons you have. Fluorine is in group 7A, so it has 7 valence electrons. To draw the symbol, you're going to draw the F, which is the element symbol. Then you're going to go around and fill in 1 dot per side until you've placed all your valence electrons. You don't want to pair up your electrons unless you have to. So that is the electron dot symbol, or the Lewis symbol, for a fluorine atom. I want to stress that that's the atom. We need to take 2 of these and put them together to make the structure for the fluorine molecule. If we draw 2 of those fluorine atoms next to each other, you can see where they each have an opening for an electron. That's where they're going to share electrons. So when we draw the actual Lewis structure, that's going to be represented by a single line. Now we still have to fill in all of the valence electrons surrounding each of these fluorine atoms. And that is the structure for the fluorine molecule. I'll put molecule in parentheses. So atom versus molecule. We'll get some more practice in, but I wanted to show you the whole process of how we go from just starting with the atoms to arranging them and putting them together to draw the Lewis structure for the whole molecule. So we talked about F2, that's a molecule. There are other elements that exist as what's called a diatomic molecule. So that means it's just 2 atoms that are the same. We also talked about hydrogen, which is the simplest one. All of these, so we've got hydrogen, nitrogen, oxygen, and the halogens. They all exist in nature as diatomic molecules. So you'll need to remember that. For drawing these Lewis structures, it's really helpful to know how many bonds a nonmetal atom can share. So this chart gives the typical bonding patterns for some of the nonmetals that you're going to encounter. For example, if you have a carbon in a molecule, it is in group 4A. So it's got 4 valence electrons, and it can make 4 bonds. It needs 4 bonds to achieve that stable electron configuration. If we look at nitrogen, nitrogen is in 5A. It's got 5 valence electrons. To reach that octet, which again, octet just means 8. So a complete set of 8 electrons on the outermost shell. To complete that for nitrogen, it needs 3 electrons. So it can form 3 bonds to get that done. So you can notice the pattern. The number of electrons that a nonmetal atom needs to complete its octet is the same number of valence electrons that it needs. So again, one more time for clarity. Oxygen is in 6A. It has 6 valence electrons. It needs 2 electrons to complete an octet. It can make 2 bonds. So that's all we're saying here. Now you see the asterisk next to hydrogen and boron? They don't form octets, so they're exceptions. Hydrogen can only pair with 1. It has 1 electron to share, and that's it. Boron is happy with a set of 6 electrons. So that's a little bit unusual. Everything else follows kind of the octet rule. But hydrogen and boron, they like to be kind of their own little clique there. So let's try drawing another electron dot formula. Only this time it's not going to be for a diatomic molecule. We're going to do it for methane, which has 2 different elements in it. We're going to start by drawing the Lewis symbols for carbon and hydrogen. You look at your periodic table and figure out what group carbon is in. It's in 4A. That means it's got 4 valence electrons. The symbol for that is going to be the C, and then 1 dot on every side. Hydrogen is group 1A. It's just going to have a single dot. The carbon is going to need 4 hydrogen atoms to have a complete octet because it needs 4 more electrons. And you can see in the chemical formula, methane is CH4. Now you may be wondering, how do you figure out which atom goes in the middle? The central atom is going to be the atom in the formula that you have the least number of them. So we've got 4 hydrogens and only 1 carbon. That means the carbon is going to be in the center. So if we draw in our electrons, that's what it's going to look like. And then we can replace those dots with single lines. And that is the Lewis structure for methane. Here's some examples of different Lewis structures. So we did the methane Lewis structure together. I showed you the Lewis structure for ammonia a few slides back. And then here's another one for water. So these are just examples of different Lewis structures. Here's a learning check. I would suggest that you pause the video and give this a try. It's always good to kind of test your understanding, because if you don't understand, you don't want to just keep watching the video, because everything builds. If you don't understand the Lewis structures, then you're not going to be able to follow the next section. So make sure that you understand, at least it makes a little bit of sense. You may not be ready to take a test, But the concept shouldn't still be super crazy, like, whoa, I don't get this. If it is, then you need to take it slow, run it back, or send me a message using course messages. Obviously, we're going to talk about it all on Tuesday, but you don't want to be in a position of watching the lectures and being like, nope, this is way beyond me. Okay, so hopefully you pause that. Now let's draw the Lewis structure for phosphorus trichloride, which, if you watch the first section of chapter 6, you should be able to name that molecule. So this molecule is actually used to prepare pesticides and flame retardants. Two kind of very different things, I know. So the first thing we're going to do is start by writing our Lewis structures for phosphorus and for chlorine. Phosphorus is in group 5A. Chlorine is in group 7A. We've got 5 valence electrons for phosphorus and 7 for chlorine. We draw our symbols in by going around until we've placed all our valence electrons. And again, you don't want to pair up unless you have to. So those are the structures for just the individual atoms. Now we need to figure out which one of these is going to be the central atom. There's only one phosphorus atom, so that's going to be the central. You're going to go with the atom that has the fewest number of them in the molecule. That is the central atom. We've got 3 of these chlorines here. So I'm going to bond each of them to the phosphorus. Then I'm going to draw in all the lone pairs. So phosphorus needed 3 bonds, and it has 3 bonds here. Each chlorine needed 1 bond, and they each have 1 bond. But we've still got these pesky little valence electrons that you have to draw in. So don't forget about these. The purpose of the Lewis structure is to show the arrangement of the atoms and also valence electrons. So phosphorus has a lone pair. Even though it is bonded to 3 other things. So that is the Lewis structure for phosphorus trichloride. Practice makes perfect. So just practice, 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 and work on your chapter 6 homework. So those were single bonds. You can also have double and triple bonds. You form double and triple bonds when you don't have enough electrons to complete octets. A double bond occurs when you share 2 pairs of electrons, and a triple bond occurs when you share 3 pairs of electrons. So we've got some examples. This is CO2, which you should be able to name. Carbon dioxide. And you do not know how to name this one. Well, you sort of do. We kind of covered these with the polyatomic anions. So don't worry about the names, but that's practice. Whenever you see a molecule that you think you can name, you should name it. And as you see here, for each of these, say for example, between the carbon and the nitrogen, we've got 6 electrons. Ooh boy. So that means that it's going to be a triple bond. Remember, each 2 electrons between 2 different atoms is going to be a single line. Now we talked about the octet rule. I told you that boron is an exception in terms of how many electrons it wants. Same thing with hydrogen. There are nonmetals that can form compounds with more than 8 electrons. They can have 10 or 12 valence electrons. And for example, you can have SF6, which you should be able to name. That's sulfur hexafluoride. Clearly, far more than just 8 electrons for the valence for sulfur. These are exceptions. Recognize an exception, but you don't need to be able to determine whether or not you should write an exception or not. So don't start taking sulfur and making it have 12 valence electrons willy-nilly, okay? So that's Lewis structures, showing the bonding between atoms and the remaining lone pairs or valence electrons surrounding those atoms. Let's talk more about the bonds between the atoms. That is related to electronegativity, which directly informs the polarity of a bond. Electronegativity is pretty much the ability of an atom to attract an electron. Electronegativity increases as you go from left to right across the period. And you may want to add this to your periodic trends periodic table. If you did that like I suggested you do for chapter 5, you're going to want to add the trend for electronegativity for completion. So as you go from left to right across a period, it increases. As you go from the top down to the bottom of a group, it decreases. So for nonmetals, everything that's kind of over here, they have the highest electronegativity. For metals, it's very low. That kind of makes sense, because we said that metals lose electrons to form cations, those positively charged ions. If you're more willing to lose an electron, that means that you don't have the very high affinity to gain any. Nonmetals gain electrons to form anions. And this is relating what we talked about with the ionic bonding to electronegativity, okay? Nonmetals gain electrons, so that means that they must have a higher affinity for electrons. So their electronegativity is going to be higher than that of metals. I know somebody has a light bulb coming on like, what? Yes. Chemistry links together and makes sense. Here is a table of some of the electronegativity values for some metals and nonmetals and semimetals. You will not need to memorize this. It will be available for you. You'll definitely want it for your homework. So if you can, print it out and put it in your notebook or at least keep the PDF for this lecture available to you when you're doing your Mastering Chemistry homework. With the electronegativity values, we can calculate differences between two atoms that share a bond. And that difference can predict the polarity of a bond. Polarity just indicates whether or not the electrons are shared equally, not quite equally, but still shared, or if they're just completely donated from one atom to another. For example, we've got this hydrogen molecule, H2. These atoms, two atoms that come together to form this molecule, they're the same thing. So they're sharing electrons equally. We can figure out that they have a nonpolar covalent bond using the electronegativity table that I showed you before, and I'll show you how that works. But when you have a molecule like HCl, there's a bigger difference in the electronegativity of hydrogen and chlorine. So it's an unequal sharing. That's going to give you a polar covalent bond. So let's talk about these types a little bit more. Nonpolar covalent bonds occur between nonmetals. And we're talking about pretty much equal sharing of electrons by the two atoms that are bonded together. And they have a really small electronegativity difference. So like I said, that table that has the electronegativity values, it's going to come in handy here. You can look up the individual atoms, like for instance, if you have N2, well, that's two nitrogen molecules bonded together. You take the difference between each of these atoms, which are the same, so 3 minus 3 gives you 0. That's a nonpolar covalent bond. So the take home here in terms of the numbers, 0.4 or less in terms of the difference in electronegativity between two atoms, that's going to give you a non-covalent bond. Polar covalent bonds, that's unequal sharing. So they're still sharing, but let's say you have two toddlers and they are sharing a toy. I know toddlers don't really share very well. So one toddler may be holding on to a toy for 5 minutes and the other one wants to play with it. Then the other one finally gets it. And after a minute, the one who just had it wants it back, right? That's not really equal sharing. There's a moderate difference in electronegativity between the two atoms that are bonded together. So you're looking at a difference of 0.5 to 1.8. That's a bit broader than the non-covalent bonds, right? But all of these are polar covalent because you're looking at the difference between the two. And again, you're looking up oxygen and you're looking up chlorine. And you're taking the difference. So you do that for every one of these pairs to figure out the electronegativity difference. Polar covalent bonds become more polar the bigger the differences between their electronegativities. The separation of charges in a polar bond is called a dipole. So when we're talking about a polar bond, we have some symbols that we use. We use the lowercase Greek letter delta. And the atom that has the lower electronegativity gets labeled with the delta and the plus sign. And the one with the higher electronegativity gets the lowercase delta with the minus sign. You show the direction going from positive to negative. So that's why you start with a plus sign where the positive dipole is. And then you draw, or the positive end of the dipole, excuse me. And then you draw your arrow towards the negative end. So that's just some terminology and some symbols that can better characterize a polar covalent bond. Now we're going to cover ionic bonds. Ionic bonds occur between metals and non-metal ions. Again, just to remind you, because we haven't talked about ions and stuff in this part, an example of that would be like NaCl, sodium and the chlorine. And we're talking about electron transfer. So if we had that single valence electron from sodium, and we've got this chlorine that is just itching to have one more electron, that sodium is going to lose its one valence electron and give it to the chlorine. That is transfer. If you have an electronegativity difference that's greater than 1.8, you're now in ionic bond territory. So this is a summary slide. It tells you the different types of bonds. So we've got the nonpolar covalent, polar covalent, and ionic. In between 1.8 and 2, you can actually have polar covalent or ionic. It really depends on what elements are involved. So whenever you have the metal plus the non-metal, that's going to be ionic. If you've got two non-metals, it's going to be covalent. So that's just one small caveat. This chart visually summarizes all of that text. So you've got your electronegativity differences, the bond types, and how the electrons are shared, whether it's equally, unequally, or they ain't shared at all. They're just transferred. We can use the electronegativity chart, calculate the difference, and predict the type of bond. So this table just gives you some examples of doing just that. But we can practice doing it ourselves too. So here, we need to use the electronegativity difference to identify the type of bond. So we've got nonpolar covalent, polar covalent, or ionic. For A, we've got potassium and nitrogen. Right off the bat, potassium is a metal. Nitrogen is a nonmetal. So without even doing any math, I can predict this is going to be an ionic bond, because ionic bonds happen between metals and nonmetals. Metals just give up that valence electron. But we'll do the math anyway. The electronegativity for potassium is 0.8, pretty small. However, nitrogen, it's 3.0. So that's clearly an ionic bond. But again, I knew that simply by identifying potassium as a metal and nitrogen as a nonmetal. Let's use a different color for B. Here we've got nitrogen bonded to oxygen. They're both nonmetals. So I can't just choose. I know it's going to be either nonpolar covalent or polar covalent, but I've got to do the math. Here we're using oxygen and nitrogen again. And there is a difference. Since it is 0.5 to 1.8, that means that it is slightly polar. We've got a polar covalent bond. And it's really that simple. Just a little bit of subtraction. So what have we covered so far? We've covered Lewis structures, which tell us how the atoms are arranged in a molecule in terms of their lone pairs and bonding. We also know more about the bonds between those atoms. Ionic bonding, nonpolar versus polar covalent. Now we're going to combine those ideas to talk about the shapes and polarities of whole molecules. To do this, you first have to learn about what's called VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory, and it describes the orientation of all the electron groups around that central atom. So let's say that we had our methane. That's the Lewis structure. That carbon is the central atom. All of the hydrogens are considered electron groups. So that's what the VSEPR theory describes, how these things are arranged in space. The electron groups are going to be arranged so that they're all as far apart as possible while still being positioned around the central atom. Remember, electrons are the same charge. They're negative. They repel each other. So they're going to be as far away from each other as possible while still forming bonds with that central atom. The specific shape of a molecule is determined by the number of atoms attached to the central atom. It also involves the number of lone pairs, which we'll get to that in a minute. Now we're going to go over the different shapes. So there's a chart that summarizes all of this, but make sure that you get that chart in your notes because it's going to summarize all this stuff. You may want to jot down some notes about each of these groups, but don't worry too much about copying down every single word on this slide because there is a chart that summarizes it. So first we're going to talk about a central atom with 2 electron groups. So our example here is carbon dioxide. If you draw out the Lewis structure, you're going to have the carbon in the center and then an oxygen on either side. There's not enough octets, so you're going to form some double bonds here. When you have 2 electron groups, the furthest apart that they can be is 180 degrees. So if this is your oxygen here, and this is your other oxygen, if you ever had these ball and stick model kits for chemistry, particularly for organic chemistry, then you'll understand the red is always oxygen, the black is carbon. That's just, if you recognize it, you recognize it. If you don't, you're not going to be hurt by it, okay? But these oxygens are spaced 180 degrees apart. The shape that we're going to assign this is linear. So we've got a central atom plus 2 electron groups. Again, you don't have to bother to write this down yet. There's a chart. Now let's talk about a central atom with 3 electron groups. That example we're going to use formaldehyde. So formaldehyde is, if you've ever taken AP Bio, if you've ever done dissections of like a fetal pig or a frog or anything like that, formaldehyde is one of the agents that's used to preserve. Kind of stinky stuff. There's also formaldehyde smell in like new carpets. So if you ever lived in an apartment where they just put down fresh carpet, that's part of the smell that you're smelling. It's formaldehyde. It's kind of a yucky smell to me. Anyway, if you have 3 electron groups placed around a central atom, you're going to, again, minimize the repulsion by placing these groups far apart. The best you can do is have a bond angle of 120 degrees, which is trigonal planar. It's like a peace sign. So if you can remember that, that'll help you remember trigonal planar. I'm pointing out the number of electron groups and eventually electron groups in lone pairs because this is the best way to figure out the shape using Vesper theory. So again, we're going to be combining drawing Lewis structures, identifying electron groups and lone pairs, and then identifying the shape that the molecule has. So that's just the forward glance. We can also have 3 electron groups where we've got 2 bonded pairs and 1 lone pair. The bonded pairs are the atoms bonded to the central atom. The lone pairs are just the lone pairs around the central atom. Those electrons have to be somewhere too, and they're going to contribute to the repulsion between the different electron groups, so the bonded pairs. You've got to place these as far apart as possible. But in this configuration where you have 2 bonded pairs and 1 lone pair, still 3 electron groups, but one of them is a lone pair, you have a bent shape. So I drew in that lone pair for the sulfur. It's just hanging out up there. So know the difference. There's still 3 electron groups, but one of them is a lone pair. And that's the difference between having a bent shape, like in this case, and the trigonal planar in the other case where you had 3 electron groups that were 3 bonded pairs. Now we've got 4 electron groups. Back to using our example of methane. To minimize the repulsion, you're going to place all of those at the corners of a tetrahedron. You've got a bond angle of 109 degrees. And so if you draw it with the wedge and dash to show, which one's coming out at you versus going back into your computer screen or what have you, it's going to show you kind of the 3D geometry. But it looks like a pyramid. So anytime you see that, the 4 electron groups where there's all four of them are bonded pairs. You're going to make that pyramid. You can also have 4 electron groups by having 3 bonded pairs and 1 lone pair. And in the case of ammonia, NH3, that's what we have. So if you draw the Lewis structure, you've got the nitrogen in the center, it's bonded to 3 different hydrogens, and it's got a lone pair. That lone pair is going to influence the shape of the molecule, just like the hydrogen bonding. This one is also going to form something that looks like a pyramid, but it's called trigonal pyramidal, because instead of having an atom up here at the top, you have a lone pair. So it's got the trigonal shape, only 3 things here, but you've got that lone pair up top. So make sure that you know the difference between these two. Again, lone pair versus bonded pair makes a difference with the shape. We can also have 4 electron groups that are broken up as 2 bonded pairs and 2 lone pairs. In the case of water, that's what we have. The Lewis structure, you've got oxygen in the center. You've got the 2 hydrogens bonded to that oxygen. And oxygen has 2 sets of lone pairs. So it still looks like a pyramid, but the shape is bent because the shape is really dependent upon the bonded pairs. So we have 2 different types of bent. And I'll show you that in the table. So this table is going to be super helpful to you. All of the things that we covered are in this table. So print it out, put it in your notebook. Make sure that you know the difference between those bonded pairs or bonded atoms and lone pairs, because that will be the difference in some of these shapes. There are 3D models of the examples that we went over. So make sure that you understand these shapes. Now we're going to go through and give an example on how to predict the shape of a molecule. The first thing you're going to want to do is start with the Lewis structure. That's the best way for you to figure out how many electron groups you have and how many of those are bonded pairs versus lone pairs. Hydrogen has 1 valence electron. Sulfur has 6 valence electrons. Remember, we're looking at the group number to figure that out. So just a hydrogen atom, hydrogen with a dot. Sulfur, we've got 6 dots. Now we've got to arrange these. Our central atom is going to be the sulfur, because when you look at the formula, there's only one of those. So let's start by bonding the hydrogens to the sulfur. Then we've got these lone pairs left over. We've got 4 electron groups. And when we break that down, we've got 2 lone pairs and 2 bonded pairs, which in the table is bonded atoms. They're the same thing. You're not going to have this table for the exam, but use it to practice so that you can remember. So if you have to make flashcards or something like that, so that you can remember the shapes and the number of bonded atoms and lone pairs associated with it in the bond angle, do it. Flashcards are great for memorizing information like this. So if you're looking at the table, you know you've got 4 electron groups. So that means we're looking somewhere in here. Now you've got to find the shape that has 2 lone pairs and 2 bonded pairs. So we're looking at bent for the shape. Let's do another one. So this is a learning check. If you feel comfortable, you should pause it and try it. If not, work along with me. As always, we start with drawing the Lewis structure for each of the atoms. Phosphorus is in group 5A. It's got 5 valence electrons. That is its Lewis structure. Fluorine is in group 7A. That is its Lewis structure with 7 valence electrons. Now we're going to arrange these to form the Lewis structure. Fill in all your lone pairs, especially the ones on the central atom, because that's going to tell you your shape. So for the question, we've got to determine the number of electron groups and lone pairs. So we've got 4 electron groups. One of those is a lone pair, which means that we have 3 bonded pairs. Then you're going to look at your chart, or if you use your flashcards, you're going to figure out, okay, I've got 4 groups. Three of them are bonded, 1 is a lone pair. So that's tetrahedral. Or oops, look at me circling the wrong thing. Leading y'all astray. It looks like a tetrahedron. But the shape is trigonal pyramidal because we've got, let's see if I can draw this pyramid. We've got a lone pair as one of the points. So we don't count that when we're looking at the shape. Let me draw that shape a little bit better. So this is the P. Then we've got the F's down here like that. And then the lone pair up top. Don't make the same mistake I did, which I was just lazy and just circled the wrong thing. But look at the chart and make sure that you understand which one you're choosing. So knowing these lone pairs versus bonded pairs is really the key to choosing the correct geometry. The final concept that we're going to cover is polarity of molecules. So we've already talked about the bonds between atoms. Now we're going to talk about the whole molecule. So the different bonds that create the molecule. With nonpolar molecules, they're nonpolar because they have all nonpolar bonds. But you can have polar bonds and still have a nonpolar molecule. Going back to our dipoles, the CO bond is polar. It's polar covalent. But the direction of the dipole matters. The direction and the shape of the molecule. CO2 is linear. So you're going to have some negative charge out this way and negative charge on the other side 180 degrees away. Those two cancel. In CCl4, carbon tetrachloride, you have 4 different electron groups and it's tetrahedral. The carbon to chlorine bond is polar, but because of the direction of each of those, you cancel out all of the dipoles. So it's a nonpolar molecule. So remember those examples. That'll help you when you're figuring out whether or not a molecule is nonpolar or polar. With polar molecules, you've got one end of the molecule that's more negatively charged than the other. And if there are polar bonds involved, they don't cancel each other out. So we're looking at unequal sharing of electrons. The difference in electronegativity between hydrogen and chlorine is a decent amount. So you're going to have far more of your electrons over here than over here. That's unequal sharing. That single dipole is not going to cancel out. So this is a polar molecule. You can also have a polar molecule if you've got 2 lone pairs and 2 bonds around the central atom. And if you remember your shapes, that's one of our bent shapes. These dipoles in water don't cancel out because you've got the convergence of all that negative charge right here for the oxygen. So there's a partial negative on the central atom, and you've got partial positives out here. So those don't cancel. You've got a polar molecule. Another configuration where you can have a polar molecule is 1 lone pair and 3 bonds. That's trigonal pyramidal for the shapes, the Vesper shapes, where you've got a lone pair and 3 bonded atoms. Those dipoles do not cancel out. They all converge on the nitrogen, if we're using ammonia as an example. And then we've got all that positive charge for the hydrogens. So these don't cancel out, and you have a polar molecule. So let's try an example. Let's determine whether a molecule of OF2 is polar or nonpolar. For extra practice, you can name it because you've got two nonmetals. Yes, I'm throwing in the extra practice because you need it. Why not? It's a gimme. The first thing you want to do is figure out what kind of bond you have between the oxygen and the fluorine. Fluorine, you've got 4.0. Oxygen, you've got 3.5. Their difference is 0.5. That means you've got a polar covalent bond. Great, we figured that out. But we're not done. Now we need to figure out that Lewis structure and the shape. We know that we've got a polar covalent bond, so we've got some dipoles happening. But now we need to know whether or not those dipoles cancel each other out, or if they don't. Oxygen is in group 6. I'm just going to go straight to drawing the Lewis structures for the different atoms. Group 6 means 6 valence electrons. Fluorine is in group 7, so it's got 7 valence electrons. When we put them together, we're going to use oxygen as the central molecule because there's the fewest of them. We're going to bond that oxygen to both of the fluorines. Then we're going to fill in all of our lone pairs. For electron groups, we've got 4 electron groups. Two of them are lone pairs, and 2 of them are bonded atoms or bonded pairs. That means we're going to have a bent shape. So when we think about our dipoles, we're not going to have any kind of canceling out because we've got parts of the molecule that are negative, more negative, and parts that are more positive. That means that this molecule is polar. So that kind of summarized all the things that we did to get to this point of talking about the polarity of a molecule. The Lewis structures, the shapes, the different bond types, and how those bonds are rearranged in space to create a polar or nonpolar molecule. The final section for this chapter focuses on the forces between molecules, which are the intermolecular forces. So far, we've been talking about the intramolecular forces. So that's talking about the internal forces between the atoms in a molecule. Intermolecular means that you've got multiple molecules interacting together. So in a glass of water, you've got intermolecular forces that govern the properties of that liquid water. Let's cover the different kinds of intermolecular forces that you can have. In a covalent compound, polar molecules have these intermolecular forces called dipole-dipole attractions, or dipole-dipole forces. Remember when we were looking at the polar covalent bonds that we have a dipole. If we use HCl as our example, the hydrogen is the partial positive and the chlorine is the partial negative. Well, if you have a bunch of those together, then the partial negative is going to attract the partial positive from another molecule. That attraction is called a dipole-dipole attraction. You can also have hydrogen bonding. And hydrogen bonding is between hydrogen and fluorine, oxygen, or nitrogen, or lone pair with either of those three atoms. So this is like a specialized, strong dipole attraction. Hydrogen bonds are actually really important because they play a huge part in the structure and shape of DNA, which is the blueprint for your cells. So the cells all have a nucleus, which has your DNA, and there's proteins in there that help maintain the shape of the DNA, but there's also hydrogen bonding. And that hydrogen bonding keeps the spacing right, keeps the shape right, all kinds of things. So hydrogen bonds are very, very important biologically. You're going to want to know the difference between just regular dipole-dipole and hydrogen bond. We can also talk about dispersion forces, and that's the attractions between nonpolar molecules. Remember that these molecules are not just sitting in space, they're moving around. Even in a solid, there's some vibration. So it's not a whole lot of motion, but there's still some motion. In liquids and gases, you have more and more motion. When molecules bump into each other, they can cause temporary dipoles, which means that you've temporarily got the nucleus maybe on one side and the electrons on the other. And so you've got some attraction between the nucleus of one molecule, of an atom in one molecule, and the electrons in another. Those forces are pretty weak, but it enables nonpolar molecules to form liquids and solids. One example of a liquid that is a nonpolar molecule would be gasoline. Gasoline is just a hydrocarbon. There's hydrogens and carbons. That's it. Very nonpolar. But it's a liquid. The forces that allow those molecules to interact with each other are dispersion forces. The reason we care about these intermolecular forces is because they influence the properties of different compounds. The strength of the intermolecular force gives you an idea of how high the melting point will be. So if you have a lower melting point, you're going to have dispersion forces. It's just weak forces holding that compound together. If you've got a weak force holding stuff together, it's not going to take a whole lot of heat to break them apart. If you've got stronger intermolecular forces, like hydrogen bonding or dipole-dipole interactions, you're going to have a higher melting point. The highest melting points are for those with ionic compounds. So those intermolecular forces are even stronger than the hydrogen bonds. And this table kind of gives you examples, and it gives you the different types of interactions. Starting with the weakest force, and these are the intermolecular forces, all the way up to the strongest. So you'll want to remember this relative order and how it relates to melting point. Weak intermolecular forces, low melting point. This chart gives you a nice summary of the types of forces between atoms or atoms or ions in this top part, and then between molecules, because we need to relate all of this information. We talked about ionic bonds and covalent bonds in the first part of chapter 6. So that was the first video. Those ionic bonds are going to be very strong. We talked about the forces between molecules just now. So we talked about the arrangement of the molecules, dipoles, polar covalent, nonpolar, all of those things. We're talking about the arrangement of the atoms, and then how those arrangements influence how the molecules interact with each other. So you're going to want to be able to talk through this chart and understand the different trends and how they relate. Let's do one more learning check, and this is going to cover the intermolecular forces that we just talked about. We're going to use all the information at our disposal to determine whether the intermolecular forces holding these liquid compounds together is ionic, dipole-dipole, hydrogen bonds, or dispersion forces. For part A, we need to figure out what kind of bond we're looking at. We've got two nonmetals, so it's going to be a nonpolar covalent or it's going to be polar covalent. Nitrogen and chlorine have the same electronegativity. So we're looking at something, getting all excited here. We're looking at nonpolar bonds here. So that's talking about the N to Cl. For nonpolar bonds, we're looking at dispersion forces when we're talking about the molecules. So NCl3, it's comprised of nonpolar bonds within the molecule. So the molecules themselves, when they're interacting with one another, we're talking about dispersion forces. H2O, and I'll use a different color. When you figure out the electronegativity difference, we're looking at polar covalent bonds. And this is talking about the water molecule. Within the water molecule, the H2O bonds are polar covalent. We know that the arrangement of water means that we've got a polar molecule on our hands. For those, we're talking about hydrogen bonds. The key, without even going through the calculating the polar covalent bonds and all that stuff, we've got a hydrogen bonded to oxygen. That is a hydrogen bond. Having bond with hydrogen bonds. Sounds terrible. But that is a way to remember fluorine, oxygen, and nitrogen form hydrogen bonds. Okay. You can do it the other way too. That's why I showed it. You can reason it out if you don't remember this silly mnemonic. Now we're going to move on to Br2. Right off the bat, we can tell that this is a nonpolar molecule. And when we're dealing with nonpolar molecules, the forces between those molecules are dispersion forces. Last but not least, we've got KCl. Now we already see potassium is a metal, chlorine is a nonmetal. So that clues you in that we're looking at ionic bonding here in general, and that the interactions between these molecules is also going to be ionic. But if you wanted to look at the bond between the potassium and the chlorine, you could. And it would tell you that you have ionic bonds here, which would tell you how the molecules would interact with one another. Again, this is relating the information that we learned about the bonds between atoms to how the molecules interact with one another. So when you're doing this type of problem, you don't have to go all out like I just did and write out all this information. I wanted to link it together for you so you can see how they relate. No real math here, but definitely a fair amount of concepts. And the biggest tidbit of help I can give you is to focus on the summary charts. If you can explain and use the summary charts, then you'll be in good shape for the exam. This is the concept map for Chapter 6. We talked a lot about ionic compounds in the first video when we did naming. We talked about the positive ions, negative ions, how to write formulas from names. With the molecular compounds, we talked more about those in this part, in part 2 of the Chapter 6 lecture, where we talked about the Lewis structures, the shape, electronegativity, the different types of bonds, so polarity of bonds, polarity of molecules, and then how those molecules interact with each other, also known as intermolecular forces. So this flowchart may help you kind of put all the things together that we talked about and see how they're related to one another. As always, reminders. If you watched the first video, then you already got these reminders, but I'm going to put them in again. You have exam 2 coming up, and it covers chapters 4 through 6. It's going to be available on Wednesday, October 7th in the morning until Friday, October 9th at 11:59 p.m. I will provide the periodic table and all the other acceptable materials in the exam 2 folder in course content. Make sure that you print those before you take the exam. You are allowed to use a calculator that is not your cell phone. And you can also have some scratch paper to kind of jot down your notes or to work out problems. But you will not be required to upload your work this time. This exam is very concept heavy. You have Chapter 6 Mastering Chemistry homework and quiz. That's due on Sunday the 11th. So you have a couple of days between the last available time that you can take exam 2 and when your Mastering Chemistry homework is due. I would advise you to take advantage of the homework, where you get multiple tries, to learn the Chapter 6 material. And because you have an exam and Mastering Chemistry, there's no chapter check-in for this week. I want you to be able to focus on studying for the exam. With that said, good luck, and I'll see you in class on Tuesday.